Hello everyone, welcome to the new lecture of Motion Control Systems class. Today we will have a relatively short lecture about the implementation details of the controllers. I have been receiving a lot of mails from you on the lack of enough number of examples, which will be compensated in about 3 weeks during the mid-May period. But before we move on with the rest of the topics, because we have 2 weeks left for the remaining class material. Before we move on with that, I want to show you how you can realize a controller in real time. So before we go for the derivation, let's recall the structure of motion control. Structure of motion control implementation. Because I have received a lot of complaints from you telling that it's good to learn everything on paper, but how to realize these in real life? How can we implement those algorithms in real applications? That's why I wanted to prepare this lecture slide set for all of you. Now, if you remember the structure of motion control system, I have been drawing this in the previous classes, and I would like to highlight it once more. What you have here is a plant. Let me change the color, by the way. Okay. You have here a plant which actually gives you some measurements, let's say Q, and this measurement is obtained through a system that's called encoder. Let me write here encoder. So you have your measurement from the encoder, and this plant requires a lot of power to be driven. So in order to supply this power, what you need is somewhere here the driver unit. Okay, this is your driver. What your driver does is to take the power from a power source, so the energy comes from the power source to the driver and is used in a useful way to drive your plant. So that's high energy power flow. But what we have usually is this. We have somewhere here the digital controller. Let me write here the digital controller. So there are many different brands in today's market where you can use which have actually the different types of digital controllers. There are many different brands, and that's one of the common implementation methods for running the robotic systems. Now, what you have is this. If you have an encoder gives you the position signal Q, and you have the digital controller that receives that encoder input from a counter channel. Let me try to also highlight this for you. Okay, this is counter channel of your encoder. Okay, that one is better. So if you have, for example, 5 different motors to be controlled simultaneously, you would need at least 5 counters, one for each encoder of the motor. Okay? But that's not all of the information here, all of the channel numbers. So we will basically have some different units here. Let's have here a digital to analog converter. So this digital to analog converter is responsible to convert the digital signals created inside your algorithm to analog output value, and it's between plus and minus 10 volts. That's a common industry standard. There are different DUC implementations where you'll find, for example, plus minus 5 volts or different range. But usually the industry standard is plus minus 10 volts for the analog signal. And what happens is that your driver receives the analog voltage input from your DUC channel here and adjusts the power accordingly. So plus minus 10 volts corresponds to plus minus I max. So you can think of it as a way to scale the power. For example, 0 volts corresponds to 0 current at the plant. Plus 10 volts corresponds to plus maximum current, so that's maximum torque on one direction, and minus 10 volts corresponds to minus maximum current, so that's the maximum torque but in the reverse direction. So basically you have here a low power signal. This is, change the color, this is low power signal, and it's just for the digital controller to send a signal to the driver to warn it about the amount of current or amount of torque to be applied on the plant, and plant is basically your motor. However, this one and this one is high power signals. So, and this is also a low power signal, by the way. Your encoder response is also very low power signal. So it can be considered this way. Your power source and the high amount of power coming from the power source guided by the driver onto the plant is the high power side of the issue. But as your plant runs, it also rotates or moves. If it's the linear plant, it either rotates or moves in linear way the encoder, and encoder is just a readout circuitry. It reads the pulses and tells you how much pulses passed. Based on the difference between two consecutive pulses, you can understand your amount of deflection, amount of motion. So it's important to understand what happens here in digital controller side, because I have left a lot of spaces here empty. For example, if your system contains, let me go back to the original color. If your system contains a force sensor somewhere here, let's put it there, force sensor, and your force sensor, let's suppose that your force sensor gives some analog data. So this is analog data. In order to receive this data in your application, in your code, you have to take it from the analog to digital converter channel of your controller, because your original signal is an analog signal. Let's say it's between plus and minus 5 volts, and you should be able to convert this plus and minus 5 volts to some numerical value so that you can run it in your digital controller side. So that is what happens in reality. This is the real-time implementation. But I would like to draw your attention on one point. Now, the moment you give a signal here to the driver, the driver is basically a current control unit that takes the reference signal from here and adjusts the output in such a way that it matches with the reference signal. So if let's say Imax is, let me give you an example here. So example, let's assume that Imax is 3 amperes, and you give to your system as reference here from the DAC channel some, let's say, 6 volts. Reference is adjusted as 6 volts. So what happens is that 6/10 is the rate of input, so that's actually 60%. Let me show it in a better way. This is plus 60%, right, of maximum power. So what you have is that this is your maximum current input and it's 60%. So your driver output will be 1.8 amperes reference to the motor. So that's a simple example to illustrate how things are going. So basically your digital controller adjusts the output voltage in the DAC channel, and your driver, based on the reference value in the DAC channel, adjusts the power from the power source to the plant. That's a general systematic. Now, one thing is important. The moment I supply here 1.8 amperes, I know that, for example, further assume that K nominal is, let me say, 5. So that's actually 5 Newton meter per ampere, right? So tau reference is equal to I reference, if you remember, times K nominal, right? So this is 1.8 amperes times 5 Newton meters per amperes, right? Which gives you tau reference as 9 Newton meters at the output. So with 6 volts of reference signal, you create 9 Newton meters of output in that system. Here, your plant's reference torque is 9 Newton meters. Now, the question is that we should act, I mean, how fast should we act? So if we give the 9 Newton meters of reference to your plant, to our plant, as is, and do not change it, so we know that it's going to start rotating to a certain direction and will continuously rotate until its equation of motion is balanced, until the friction and all other forces balance this 9 Newton meters at certain speed. But what we want is control action, and control action is in closed loop. So we have to have this loop. Let me change the color. Okay, we have to have this overall loop to be run very fast. And The time difference between every two consecutive loop iteration is referred as the sampling interval, sampling time, dt. Okay. Now, these are all information you already know from our previous classes. Let me write here the time difference between every two consecutive iterations of real-time loop is the sampling, let me say here, is called the sampling frequency. Sorry, sampling period. And frequency is 1 over period, if you remember. So that's basically dt, right? So for all practical purposes, we want dt to be as small as possible. So one note is, so let's write here, precise motion control requires dt to be as low as possible. So dt should be as low as possible, which means that sampling frequency should be as high as possible. So let's write it also here. The sampling frequency should be as high as possible. Well, sampling frequency is also referred as the frequency of the control loop. Don't forget this. And let me try to explain why this is important for us. Look at this loop back. Of course, on this plant, there are some disturbances acting directly, right? So this. Now, if you want to compensate those disturbances, suppose, of course, these disturbances are not static, they're dynamic disturbances, and suppose that the disturbance varies in time. So, in order to compensate those variations precisely, you have to catch you have to be able to catch very small amount of variations also. This requires from you to have a very high frequency loop iteration here. Let's say if you're running at 100 Hertz, this means that in 1 second you're running this loop 100 times. Between every two consecutive iterations, you're going to have 10 milliseconds. And in 10 milliseconds, many things might change in a motor. So if you increase this to 1 kilohertz, which means 1000 times per second, then your dt reduces to 1 millisecond, which means that before every two consecutive iterations, you just put a time delay of 1 millisecond. And in 1 millisecond, it's really hard to create big disturbances in your plant. So that was our motion control structure. But I would like to also highlight the difference between, let's write here, difference between real-time, or let me say here, let me write here, actual implementation and simulation is the realization of plant. Well, what I mean here is this. If you are running an actual scenario, you have the plant naturally existing in your system. So plant exists naturally. What I mean is that whatever current you give to your plant, you see it moving, and you can take your readout from your encoder to your counter circuitry in the digital controller. But in simulation, plant should be created in virtual environment. So what you need is, in simulation, you have to give or simulate the model of the plant. And if you remember, we have been doing this many times. So here is what we have. You give the input current IRF. It's like a big black box here, the plant, and you have the response here, Q. But in simulation environment, you basically, and of course don't forget that on the plant there is naturally a, well, let me move these to the new page so I can show you a better illustration. Let's move to the new page. So actual scenario, is this. You give your input as IRF to your plant, and what you have here is that there is the disturbance tau, this acting on the plant, and you don't know what this is in reality. What you have is just Q output from your plant. So it's like a black box. And in simulation environment, what you need is this. You're again giving the reference current to your system, IRF, but this black box here is a well-known structure. If you recall, actually, it's nothing but multiplying with K nominal, right? Because the reference current is being multiplied with K nominal to give us the torque input to our system. So you have tau reference, and here tau, this comes, which actually goes to our system with a negative effect. So it creates a negative torque here, and then this response is divided by your mass, by the mass of your system or the inertia of your system, and is being integrated and once more integrated to give you the output Q. So in simulation environment, you need to create this block. So this is in actual scenario and this is in simulation. So in simulation environment, you need to create the content of this black box yourself. The same current, the same tau, this might be affecting your system, but the structure here should be created by yourself. And don't forget that there is effect here B of Q Q dot, for example, let's put this as a block, and it takes this and this. Also, there is G of Q if there is any gravity effect on your system. So this is what you receive. So without loss of generality, we can assume that in simulation we have that structure. And you have to have a precise model of your system, which means that you should be already having the B value, the G value, all of these values should be in your hand so that you can simulate your system. So the difference is that here in actual scenario plant naturally exists, and in simulation plant is also simulated. Plant is created in the virtual environment. Well, how can we make real-time implementation or simulation? Let's discuss this. So question, how can we realize a motion control system either in simulation or in real-time implementation? So this question is actually a little bit detailed question. I would like to I would like to draw your attention on one point. Until now we have been driving our controllers all with the derivations made in S domain, and you know we were carrying out our calculations either in time domain or in S domain. I'm sorry. So both of those domains are actually continuous domains, and if you'd like to implement the controller, remember this structure here. That structure runs in digital environment, and we need to have a discrete way to implement these controllers, these algorithms. So the problem is that problem modeling and derivation is made in continuous time systems. That's either f of t in time domain or f of s in Laplace domain. Both of them are continuous time implementations or continuous time derivations. But the realization is made in discrete time. We sometimes call this f of z. So there is the z transform notion here. I'm going to cover this with you. So this is z transform. Sometimes this discrete time is also referred as the digital implementation. So we should learn how to move from continuous to digital implementation. So how can we move from continuous to digital? This is an important question in mind. So for this actually we will cover the method of Z transformation, but let me try to express it in different words. Now, the digital control, the design of controllers in digital environment by itself is a whole chapter, is a whole series of lectures. It's actually a graduate level class in many universities. That's why we don't have this much time to go over every different step or every different to cover all of the aspects of the digital or discrete control structures. But here I'd like to just draw your attention on the way to move to digital environment. So that's why I wrote here, how can we move from continuous to digital? And it's through, so let me write your answer. It's via proper discretization methods. So I will cover here one very important method, that is backward Euler method. So backward Euler or backward Euler method is a commonly used discretization method in many different control systems and in many different applications of signal processing. So this backward Euler method actually takes a function with S to alpha and converts it to the Z domain. Let me write here, in a sense it's Z transform, and maps it to 1 minus Z2 minus 1 over T to alpha. So what's this? S to alpha is being mapped to 1 minus Z2 minus 1 over T to alpha. Let's try to put more focus on this. So here your function f of s is given as s to power alpha, which is being transferred to Z domain as f of z, that's the digital controller side, is being expressed as 1 minus Z2 minus 1 over T to power alpha. And here some notes come naturally. This T is nothing but the sampling period. So it's the time required between two consecutive implementation steps. And here Z2 minus 1, that's nothing but 1 over Z operator is standing for unit step delay. So it means wait one step and then act in the next step. Okay. So with this, it's really hard to understand how we can realize the continuous time functions in discrete time. In order to make everything clear, I'll go over some examples. So examples will cover differentiation, integration, integration. Let's write here the third item to be, let's have here low pass filtering, And I'll try to give one last example on an arbitrary continuous time transfer function. So at every step we're going to cover three main at every implementation we're going to cover three main steps. Let me write them here. Method is here. Given continuous transfer function move to Z domain by proper transformation. In our examples, we will stick up with the backward Euler method, where S is being represented as 1 minus Z2 minus 1 over T. And second is this. Make, or let me express it differently, create input output relationship to formulate an algorithm. This part is tricky. All of the implementations will be made following these two methods, these two schemes, and the examples will cover differentiation, integration, low-pass filtering, and arbitrary continuous transfer function, continuous time transfer function. Let's start with the first one. Okay, well, I usually like this yellow color a lot. Let's write here example 1. Given f of s, so our example was on differentiation, right? So f of s is equal to s. This is the differentiation. Then f of z, the okay, let me segment it. So step 1 is given continuous transfer function, move to Z domain by proper transformation. Let's do it. F of Z is 1 minus Z2 minus 1 over T, right? There is no alpha here. The hidden alpha is 1, and I put here hidden power as 1. That's what we have. And item number 2, create input-output relationship to formulate an algorithm. Let's write it. Step number 2. So f of z, which is 1 minus z2 minus 1 over t, should be equal to y of z over u of z, right? So this is output over input, like the transfer function notion. So if you remember, this s is nothing but y of s over u of s, right? Now, if we make some manipulation here, if we make the cross multiplication, what we have would be y of z times t should be equal to u of z minus u of z times z2 minus 1. So if you have a look at here, this z2 minus 1 item, that multiplier, z2 minus 1 was referring to unit step delay, right? So here I have the function itself, and here I have the function's one step delayed version. So if you move to discrete implementation, you can write here that the algorithm is, you can actually play with this equation and write here y of z is equal to 1 over t times u of z minus u of z times z to minus 1. Okay, so algorithm is that yk, the output at the kth step, this is important for us, that part is very important for us, it should be equal to 1 over t times uk minus uk minus 1, right? So this is what the z transform tells us. Remember guys, the way we were taking derivative of a signal is equal to the new signal response minus the old signal response from one step previous sampling over dt, the sampling period. This is nothing but the derivative, right? Differentiation. So here you have the algorithm through z transform. Let's go through the second example. Our second example was integration. Let's see what we will have in integration. Example 2. This was basically integration. Let me try to stick up with the same notation here. Given f of s, the continuous time function, as 1 over s, right? This is what we have in integration. And remember, this s was being replaced by the z transform equivalent. So we should write here the first step is discretization with proper z transform. If you remember, instead of s we were writing 1 minus s to minus 1 over t. Now instead of 1 over s we should write here f of z is nothing but it's t over 1 minus z2 minus 1, right? So this is inverse of the backward Euler method. Now if you move from here to an algorithm like this, what you need is this. Let me go and write here. Okay, I'm sorry. F of z, that's t over 1 minus z2 minus 1 should be equal to output over input, as this was equal to output over input. Now if you have this relationship, then you can again make cross multiplication and come up with the following recursion. Let me write it here. Y of z minus y of z times z2 minus 1 should be equal to u of z times t. Just like what we did here, right? And it's important to leave y of z alone here. So we can write this as y of z, our output, is equal to y of z times z2 minus 1 plus u of z times t. So here we should recall that y of z is the output at this time sample, and y of z times z2 minus 1 is one step delayed output. So if we move to algorithm, we can write it here. Algorithm is yk is equal to, so what the output at the kth step is equal to output at k minus 1 step plus t times input at the kth step. Okay, now have a fresh air and think of this output. What we have here is the result of the integration, and what our algorithm claims is that our result should be equal to the previous result plus sampling time times the input acting on the system during this sampling period. So this is nothing but integration. This is just summation of the input signal to give the output signal, right? Now, let's move to a relatively more complex algorithm, low pass filtering. We have example 3, low pass filtering. Actually, we have already written it. Let's write its continuous time function given f of s is g over s plus g, right? This is nothing but output y of s over u of s. That's in Laplace domain, the way we apply low pass filtering. So then we're moving to digital implementation. Let's have a look at it. I'm gonna try to spare more space for this because it's gonna take some more. F of z should be identified, and in finding f of z, we were replacing all s values with 1 minus z to minus 1 over t, right? So we have g over 1 minus z to minus 1 over t plus g, right? Now, if we play with this equation, this is nothing but gt over 1 plus gt minus z2 minus 1. Let me try to pull these here. Gt over this. If you don't know, you can expand this. It's basically g times t here under one denominator t, and this t goes up, so you have gt there. 1 minus z2 minus 1 plus gt, so this is 1 plus gt minus z2 minus 1. That's nothing but y of z over u of z. That's the output to input ratio of our system. Then the next step was, okay, we already covered this, the second step, and the next step was that one, creating an algorithm from there. Actually, well, let me erase this and let me write the next step here. F of z is gt over 1 plus gt minus z2 minus 1, which is y of z over u of z. I'm trying to stick up with the same notation, the same method we have done in the previous examples, so that you don't have any complication in your mind. Okay, that's the way we move to discrete domain, and then what we need is to create a recursion and an algorithm from there. And while doing so, we are trying to leave y of z alone. Let's see. Y of z times 1 plus gt in this domain minus, here you have z2 minus 1, which means put one step delay. So this is y of z times z2 minus 1 should be equal to gt times u of z. Just like what we did here. And if we leave y of z alone here, so y of z should be equal to 1 over gt plus 1 times Okay, I'm sorry. So let's write it here. Okay, times, what do we have? GTUZ plus YZ times Z to minus 1. So this is Y of Z, Z to minus 1 plus GT times U of Z. That's our recursion. And from here, we can finally come up with the algorithm. So, algorithm for low-pass filtering is this. Yk, the low-pass filtered output at the time step k, should be equal to 1 over gt plus 1 times yk minus 1, one step previous value, plus gt times uk. Okay, so that's our algorithm, that's our recursion. So in the last step, I'm going to cover an example where we will have the arbitrary transfer function. So here is it, arbitrary continuous time transfer function. I'll try to make it a little bit more complex for all of you. Example 4. Hopefully I'll be able to solve it. Let's define it to be, alright, let me, okay, given f of s to be, let's have here as square plus bs over, I'm sorry, that was not my transfer function. This is as plus b over cs squared plus ds plus e, which was equal to y of s over u of s. Now, what we have here is, in the first step, we should apply a proper z transform. So f of z should be equal to, if you remember, instead of s, we were writing this 1 minus z to minus 1 over t. So that's a times 1 minus z to minus 1 over t plus b over, here we have c times 1 minus z to minus 1 over t squared, right? Plus d times 1 minus z to minus 1 over t plus e. Now, it might seem relatively, relatively hard for you, but it's not too difficult to solve this. If you try to expand this, you're gonna have this f of z is, that's actually second step, f of z is, here you have a minus a times z to minus 1 plus bt over t in the numerator, right? So let's write it here, f of z should be equal to, that's what you have in the numerator. I'm sorry, let me try to make it a little bit elegant looking. Okay, you have a minus a times z to minus 1 plus b over t. In the numerator you have this. Now here we have c times this. Let's try to find out what the square of this function corresponds to. Let's try to find out this. Okay, 1 minus z to minus 1 over t squared. So this is 1 minus z to minus 1 over t times 1 minus z to minus 1 over t. It's nothing but 1 minus 2z2 minus 1 minus z2 minus 2 over t square, right? So if you write it here with the same color, you will have c minus 2z2 minus 1c minus z2 minus 2 times c over t squared. You have the t squared term here. But let's move on with the rest of the function. And I can write here that it's plus, if you see, it's d minus d times z2 minus 1 over t. But if I multiply everything with another t, I'll have d times t minus dt z2 minus 1 over t squared, right? Then plus e t squared over t squared here. So we have this big transfer function f of c. I know it looks a little bit weird, but we can simply equate this to y of z over u of z, right? Now we can try to simplify this equation. F of z should be equal to, if you move this up, you're gonna have here at minus at z2 minus 1, right? Plus bt over t squared. These t squares will cancel each other. Then you're gonna have in the denominator the term c minus 2z2 minus 1c minus z2 minus 2c plus dt. That dt is d times t. It's not the sampling interval, it's parameter d times sampling time t minus dt z2 minus 1 plus et square. So you have this transfer function, this discrete transfer function, that's y of z over u of z. Before you move on with the rest of the equation, I would advise you to separate the numerator and denominator into components of decreasing power of z. So let's move one step ahead. I'm sorry, it says that this is the end of the slideshow. Well, I think I have to okay, we have here, well, I have to make a trick. I'm sorry, guys. Yes, keep the annotations and take some slides from here and move here and go back to the slideshow. All right, now we have the slide set again. Perfect. So we have to move from this to an organized way. So we have to actually rewrite f of c in such a way that we have decreasing powers of z. So you have at plus bt, right? So you have at plus bt here minus at z2 minus 1 minus at times z2 minus 1 over here you have c plus dt plus et square. So c plus dt plus et square, which is without any z2 minus 1 multiplier. And here you have minus 2c minus dt z2 minus 1. So minus 2c plus dt z2 minus 1 right? And finally, z2 minus 2 term, that's minus z2 minus 2 times c. So minus c times z2 minus 2 should be equal to y of z over u of z. Please take my advice and recall every time you're moving to discrete domain that if you make this diagnosis, if you separate the numerator and denominator into components of decreasing power of z, it will be much easier for you to move from this to an algorithmic output. So finally, we can write the algorithm here. The algorithm is this. So make your cross multiplication. Y of z times c plus dt plus et square minus y of z times 2c plus dt times z2 minus 1 minus y of z times c times z2 minus 2 should be equal to this side u of z times at plus bt minus u of z times at times z2 minus 1. Okay, so from this, without loss of generality, one can come up with that algorithm. Yk, the output at the kth step, should be equal to, if you basically take this to the right hand side and take this to the right hand side with all plus signs and divide everything by this, you have 1 over c plus d times t plus e times t square times let's write it this way. Y of z times z2 minus 1 is y k minus 1 times 2c plus dt, right? Plus y of z times z2 minus 2 is nothing but y k minus 2, two-step previous output value, times c plus uk, the input at this step, times at plus bt minus, here u of z times z2 minus 1 is one step delay, so this is uk minus 1, the previous output, times a times t. So that is the algorithm to implement this transfer function. So if you are given a continuous time transfer function, I'm sorry, I have to erase. Okay, if you're given a continuous time transfer function f of s as as plus b over cs squared plus ds plus e, going through all of these steps, you would come up with an algorithm to implement this transfer function in digital environment. So these will be helpful for all of you while you're trying to create your simulations. And that slide actually concludes today's slide sets. So looking forward to meet with you in our next video. And until then, take care of yourselves, please. Goodbye, guys.